Welcome to Brain Vision.
In this example, we want to figure out what temperature we have to heat the air inside a hot air balloon in order for it to just barely lift off the ground. So the balloon has a volume of 650 meters cubed, and the pressure inside the balloon is the same as the atmospheric pressure outside. So it has to lift a total of 320 kilograms of material. So that's the basket, the people inside, the fabric on the balloon. And it's doing this in air, which has a density of 1.29 kilograms per meter right here. And we're also given the molar mass of air. Okay, so what does it mean if we're just barely going to float off the ground or be suspended in air? Well, in terms of Newton's laws, that would mean that the force of buoyancy of our balloon in the air is just barely beginning to overcome the force of gravity holding it to the ground. So the force of buoyancy is just barely bigger than the force of gravity. So the point at which this is going to start happening is when they're exactly equal. Buoyancy force equals Fg. And that's just from Newton's second law, right? The sum of all forces would be equal to 0 at that moment. And we could just rearrange that equation to say that the buoyant force is equal to the gravitational force. So that equation, Fb equals Fg, let's break that down a little bit. We know the buoyant force is going to be equal to the density of the displaced air times the volume displaced, so that would be the volume of the balloon, times gravity. And this is going to be equal to, let's make ourselves a little bit more room here. Actually, here, we'll just move down. This is going to be equal to mg, where, here we go. This is going to be equal to mg, where m is the mass of all the stuff in the balloon and the people and all that, but it's also the mass of the air inside the balloon. So we'll put mass A for the mass of the air times G. Okay, so we're going to have G's cancel out here, and we're left with this equation. So we'll hold on to this for a second. Right off the bat, we can see that we know the density of air, and we know the volume of our balloon, and we know the mass of the material in the balloon. So this equation will allow us to solve for the mass of the air inside our balloon. So we're going to see why this is going to be necessary in just a moment. So remember, our original question was to find the temperature necessary for liftoff to occur. So if we go back to the ideal gas law, PV equals nRT, it relates all these properties of an ideal gas to each other, right? The amount, the temperature, pressure, and volume. And we're specifically interested in finding the temperature, so we'll solve for that just by dividing both sides by nR. And what we'll be left with is that the temperature is equal to PV over nR. Okay, so what do we know here? Well, we know the pressure of the air inside the balloon, right? I think we were calling it PB. PA or PB, they're going to be the same. We know the volume. The only thing we don't know is the number of moles here. However, if we knew the mass of the air, we could certainly get the moles of air, right? So the equation that relates moles and mass is the mass is equal to the number of moles of a substance times the molar mass of that substance. So if we had m, we could definitely get n, right? We just divide both sides of this equation by the molar mass, big M, and we'll have N is equal to little m over big M. And we could just substitute that in our equation here and be good to go. All right. So if that's the case, though, we're still going to need to figure out what this mass of air is right here. So we'll go back to this equation we first got from Newton's second law and solve for the mass of the air. So let's just write it cleaned up here. Density of air times the volume of the balloon is equal to the mass of the balloon plus the mass of the air inside the balloon. So all we have to do is subtract mb from both sides in order to isolate the mass of the air. And we'll have that the mass of the air is equal to rho sub a v sub b minus the mass of the balloon. And if we plug in those values into that equation, we will have that the mass of the air is equal to 518.5 kilograms. So now what we can do is go ahead and solve for the number of moles that we'll have, and then just plug everything into our equation for the temperature and call it a day. So the number of moles of air is going to be the mass of the air divided by the molar mass of the air. And remember, the molar mass of the air that we were given was 29 Daltons, or 29 grams per mole. Since we're going to be working in kilograms, we can just convert this to kilograms by moving the decimal place 3 times back, right? Since there are 1,000 grams per kilogram. So that would give us 0.029 kilograms per mole. So now we should be ready. Yeah, 518.5 over 0.029. So 518.5 kilograms over 0.029 kilograms per mole. You can see how the units will get moles there. And if we do that, we will get a value of 17,879 moles. So quite a bit. Okay. So now all we have to do is plug in this little n here to our master equation. Our pressure of the balloon, which is just 1 atmosphere, the volume of the balloon, which was 650 meters cubed, and then R, the ideal gas constant. And if we do that, we will end up with a temperature of 441.6 Kelvin. So quite a bit hotter than room temperature. So there you have it. We just figured out the temperature to which we'd have to heat up air inside a hot air balloon in order to lift up all the material of the balloon in the basket such that the balloon just barely starts lifting off the ground.